Okay, welcome to our next video. We're going to study the potential energy stored in an electric field. Let's say that you have two plates and those plates have an initial potential difference of, let's pretend it's V. Okay, so remember what that means. V means there's a potential difference and it's, let's say, non-zero. Let's say it's 5 volts, for example. This means that if you were to take two electrical wires and connect one to this plate and the other one to the edge of infinity, you would get, let's say, I don't know, 20 volts. And then if you take the edge of the infinity there and you connect to the other plate, you might see that there's only a difference of 15. Okay, so because one was 20 and one was 15, we would say that the two plates differ by 5. Okay, so remember, that's how we define voltage. We define it as difference between each other, but ultimately they're both being referenced to the edges of infinity, whatever that means. Okay, so now let's just go back to a generic case. We don't need a phi, we need a V, but there is a potential difference between them. This means that there's going to be a resistance to moving charge across the gap. Okay, so what I'm saying is the E field is going to be directed in the opposite of V. So let's say this is the 15 volt compared to the edge of the conversion, edge of infinity, and the other one is the 20 volt. Okay, so the higher voltage plate means the delta V is 5, right? The one on the right is higher. So that means the E field's actually pointing to the left. Remember that? It's pointing to the left. So the E vector always points away from the difference in V there. Okay, so that being said, we would assume then that this plate is positively charged compared to this plate, right? Okay, so now if you wanted to move electrons to the right, you're going to be resisting your E field, and therefore it's going to require some work. All right, so let's say that you're going to move the charge amount Q, and you're going to move it from the left plate to the right plate as shown by the arrow. So we'll label that amount as little q. Okay, so how much work would it require? Well, dW is going to always be a teensy-weensy amounts of charge times the potential difference, delta V. Okay, so we talked about how work is U final minus U initial, and that's QV final minus QV initial, or you could just say Q delta V, right? Or in our case, since we're doing a tiny amount, it's dWs and dQs. Okay? All right, so then when you integrate both sides like this, you can see what would happen. For a certain capacitor, we might not want to keep V for very long. We can just remember that capacitance is Q over V, so we could rewrite our V as Q over C. So you can always do a diagonal trade there. So what I'm saying is you could rewrite this as work equals, so that's the left side, and then we have integral of, and by V we always mean delta V anyway, so we basically would have a Q over C here, and then there's a dQ here. And I've got to be a little more careful with my capitalization here. I am transferring a small amount of the total charge, so I really should be using either a capital Q here, or I can use a lowercase q on the other. But I do believe these are the same Q, right? Same Q. Okay, so you can pull the 1 over C out if you want, like this, and then you have an integral of Q dQ. Now, what are my boundaries of integration? This is from Q equals 0 to Q equals Q final, right? So you started with no charge transferred, and then you slowly were transferring charge, maybe 1 electron at a time even, until you've transferred a total of Q final. All right, so this ends up being 1/2 Q squared. So you have 1 over C times 1/2 Q squared, where Q here now represents the total amount transferred. Okay, so anyway, this is just a new formula. It's Q squared over 2C, where Q is the capacitor's it's the charge on one plate of the capacitor. The charge on one plate of the capacitor, as I said before. Now, if this is our work, we could go back and rewrite this a couple times. So Q is equal to CV. That's another way to write it. So you could put basically Q's, you could put C squared V squared on top over 2C. And a nice way to write this, which I really like a lot, is 1/2 CV squared. Here's the reason I like this so much. This is the basically the work or the change in potential energy, and it's basically also the energy, potential energy stored in the field, as we'll learn in a minute. But this just kind of reminds me of what happens to a spring. Do you remember that F is equal to negative kx on a spring? So here's a spring, and you probably remember that x means the amount you displace it by, right? So it really means delta x. And let's say you squish the spring, you're going to basically store potential energy, positive potential energy. So let's say the spring was originally length 10, right? But then you bring it down to a length of 9. So it was length 10 and you squished it to a length of 9, right? So final minus initial would be -1. So what would happen then is you would have required a certain amount of force to do that. You'd actually have to push on it. But remember that the potential energy U final minus U initial was equal to the integral of force dot dx, right? And so the force you're applying is a constant force. You could pull that out. I'm sorry, I shouldn't say that. That's not true. You have to push harder and harder because the spring gets more and more resistant. I meant to say you're going to put in a negative kx here, dx, and then you end up with U final minus U initial equals 1/2 kx squared. And that's if you squish it from x initial to x final. And I believe you end up with x, technically in the parentheses, you actually get a k, and you have x, I think it's x final minus, let's see, it's x, yeah, this is right, x final minus x initial squared, and there's another negative there. Okay, so which means that the initial potential energy is actually, hold on, I have a negative error again. Hold on. Oh, I forgot my negative on the definition here. There's a negative here, another negative. So this ends up being a positive potential energy stored. So the amount of potential energy in the end is greater than that in the beginning. So this is big minus small, which gives us the positive. Okay, so you might remember doing that, and you basically get 1/2 k. And a lot of people just like to think of x as the amount we displaced. So instead of x final minus x initial, a lot of people like to just call that x. So notice how similar this looks. 1/2 kx squared, 1/2 cv squared, right? And so the reason this is going on is because both in the case of a spring in Hooke's law and also in the case of the capacitor, it turns out that our force is linear with distance. So kind of like squishing the spring gets harder and harder as you go, to the left on this particular diagram. In the same way, as you move the charge across, it gets harder and harder to do. So you might be pushing with, one unit of force at first, but then as you get closer, you find yourself pushing with more and more units of force. So it's a linear relationship, and we end up with something very similar to what we saw with the spring. So out of all the different energies stored in a field equation for the parallel plate capacitor, I like this one best because it just reminds me of the spring case. The 1/2 cv squared looks like 1/2 kx squared. All right, now that energy is supplied by your hand as you push the charges across, or by the device as it pushes the charges across. Now, where exactly is the energy stored? That's the question, one of the questions of the day. All right, so, well, we know in a spring system that the mass on the end of the spring and the spring itself store the potential energy in the field, right? Or stored in the spring. In our situation, we don't really have a spring. We have nothing in between these spaces, right? So let's just kind of look at the situation if you had an area A here and an area A here, right? And then you had another capacitor with a bigger plate on top, and let's say it has area 2A, area 2A and 2A. So imagine you had two bigger plates with twice the area. Well, with twice the area, as long as your distance here is the same, you really should have technically how much more how much more volume. Inside here, you have a certain amount of volume. It's area of the base, A, times D. And here you have basically 2A times D, right? So there's twice the volume, as you can see, but the plates are the same distance apart. I tried to draw them the same distance apart. So the red segments are all the same, but the plate areas are twice as big on the second drawing. All right, now we know from our formulas last time that this one has twice the capacitance. So if this is C, this is going to have 2C, right? 2C. And that's really just because the parallel plate is always epsilon naught AD when there's nothing in between the plates, right? So by doubling A, we basically doubled, by doubling the A here, we doubled the capacitance. So we know that, right? And going back to our new formula, which is 1/2 CV squared, you can see that moving charges across the smaller capacitor would require a work of 1/2 CV squared, right? And in the other case, it would be 1/2 times 2CV squared for the work. So we have twice as much work required to move the same amount of charge across. Okay, so in the first case, you push your charges across and it requires 1/2 CV squared. In the second case, you push the same amount of charge across, but it requires twice as much work. So what does that tell you? That tells you that twice as much potential energy is going to get stored. So where is it being stored? Well, the fact that we have twice the volume and it requires twice as much work tells you that it's stored in the volume somewhere. So I'll say that again. It's a little bit profound. We're wondering where is the energy stored, and we said in the first case it requires half as much energy to move this up. And so if you look at these geometrically, what is the difference between these two drawings? It is only that the volume is twice as big, right? It's only that the volume is twice as big. So we have to double our work when the volume is twice as big. That means we basically double the amount of potential energy stored in the system when we double our volume. That seems to imply that if we have twice the energy, twice the potential energy change, and also twice the volume, it seems that it's really the volume that's sort of absorbing the energy. And so this is why we say that the field holds the energy. And in many of our modern theories, we do believe that it is the field of a force that harnesses that potential energy. And in a conservative situation, we believe it can be recovered. Okay, so that's a really interesting idea. And now let's talk about energy density. Energy density. In our textbook, energy density is defined as lowercase u. And of course, like any density, it's just quantity over amount of space required. So it would be u, basically, divided by volume. Okay, so this is kind of confusing. I better go ahead and put V for volume, not V for voltage. But it's basically potential energy divided by volume. Brand new concept. Okay, so if you kind of go back to the parallel plate situation, right? Here is your parallel plate situation. We already know that the amount of energy stored in the field is 1/2 CV squared, just like a spring contains 1/2 kx squared. And we notice that the volume here is really just base area times height. So we call the distance between the plates, we don't usually call it h, we call it d, and the area of one plate is a, right? So what is the volume? Well, the volume, I can't write today, obviously I'm in a hurry, is AD, right? It's the volume. So if you want to define a new variable, lowercase u, and it's supposed to be uppercase U over volume, you would basically put 1/2 CV squared all over AD. Okay, all over AD. And then you could rewrite this and rewrite this and rewrite this and so forth. Our book does kind of do this a little bit. So they basically put the 2 on the bottom, right? So you have a CV squared over 2AD. And then if you remember that V over D was actually the E field. This is only true for between two parallel plates, but technically V is in negative integral of E dot ds, right? But when you're moving between two plates, the E field and the ds are the same, maybe opposing, but the theta is either 0 or 180, so you don't need the, let's say the theta is 180, so we're resisting the field. Basically, this becomes an EDS cos 180. We're just kind of rederiving this from last time. The cos 180 is negative 1, so we basically get negative integral EDS, and it's not positive, sorry. And then the E pops out, and that's because the field never changes between the plates as you move across, and then you're integrating ds, which means you're summing up all the displacements, and you only travel d. So it's V equals EDS, trying to convince you that again. So V over D is E, and you could kind of insert that in here. All right. Okay. Oh, and also C. Remember C for parallel plate capacitor, C was epsilon naught A over D. Okay, I meant to put that in too. So let's just plug in everything we know. So let's start by putting in the C. All right, so you have U equals epsilon naught A over D times V squared over 2AD, right? And then now you've got a D squared on the bottom. So you have U equals epsilon naught A over 2A, and the A's cancel out. Let's draw that in red. So A's cancel out. And then you end up with a V squared and a D squared here. So you end up with energy density equals epsilon naught over 2 times V over D. And then we just got done arguing that that's E. So you basically end up with this. U equals 1/2 epsilon naught, and then this is E squared. So if the work or the potential energy stored in the field is 1/2 CV squared, right, for a parallel plate capacitor, then the energy density is basically 1/2 epsilon naught E squared. So what's nice about these two formulas is they look quite similar, and that might be confusing, but it might also be helpful for memorization purposes. So what is energy density? Well, energy density is kind of like mass density, right? You have basically mass filling a space, right? You have mass filling a space, and then you basically take how much mass is in my space. So that's called rho or whatever, mass density. Or you can do charge density, how much charge is in my space. And you do Q over V. This is not, this is over volume. So man, it's confusing with two V's going on now. So anyway, you're familiar with the idea of mass density and charge density. So now the question is, can we have an energy density? Well, now that we're saying that our energy is physically stored, maybe invisibly, but physically stored in our space, it might make sense to kind of define a density for that. So that's kind of an esoteric idea, but as long as you have mass filling a space or charge filling a space, you can talk about density. Why not have energy filling a space density? So this is a lowercase u, and it's pronounced energy density. I kind of wish they'd used mu for that, but later we will use mu for something else. So, all right, kind of complicated. Okay, the next topic is dielectrics. Okay, as you know, the unit for capacitance is a farad. It is basically a coulomb per volt, as we saw in a couple videos ago. And it is Faraday who it was named after. It's probably pretty obvious. And today we want to talk about how can we increase the capacitance of a capacitor without actually changing its geometry, because all of the formulas for capital C seem to be purely geometric in their nature. Remember, for the parallel plate capacitor, the formula was a very simple epsilon naught A all over D. So A is, of course, an area, and D is a distance, right? Okay, and then for the cylindrical capacitor, that's supposed to look like a little cylinder, it was a little more complicated, but it was all geometric. It was 2 pi epsilon naught L over ln B over A, where L is the length of the cylinder. And B and A are the radii of the two plates. Remember, it's two plates. The first one is distance A from the central axis, and then surrounding that is another cylindrical plate. It should be the same length. Sorry about that. So same length. And that one has a radius B, as you recall. So that one also, purely geometric formula, right? Okay, and then the last one was a spherical capacitor, and the spherical capacitor also was purely geometric. I'll write it one more time, just in the way of review. So it was spherical capacitor, and it was 4 pi epsilon naught, and then it's AB over B minus A. And these are two concentric spheres, you recall, with radii A and B. All right, so I don't want to get too into that, but I do want to show you that besides the geometric variables A's and B's and L's and D's and capital A, there is another variable that keeps popping up, and that's epsilon naught. So the epsilon naught keeps cropping up. So perhaps if we wanted to increase our capacitance, maybe we could play around with epsilon. But how? Okay, so Faraday actually discovered something. He discovered that epsilon naught, which is what we call it the vacuum permittivity constant, that thing can be improved. That thing can be improved to epsilon in general. So you know how this means like starting amount? This is for in vacuum. I always spell that wrong. It's 2 U's. So it's 1C, 2 U's. Epsilon in general could replace all of our epsilon naughts here. And as long as epsilon is bigger than epsilon naught, we have increased our capacitance. Okay, so what he discovered was you could, between any two plates, whether they're spherical, cylindrical, or parallel plate arrangement, you could put in some kind of material between these, and that could effectively increase the permittivity in that region. So you might say, well, what the heck is permittivity? Well, permittivity is basically how it's like a number that measures how well the field is permitted. I guess you could think of it as that. Okay, so it turns out that that's probably not the best way to say it, because the higher the epsilon, actually, the less field we get. And the less potential difference we can achieve for a given amount of field. But what we can say is that it will increase our capacitance, because remember, C is Q over V. So actually, if we diminish V, we can increase C. And so there's two ways to increase C. You can either raise Q, or keeping Q constant, you can diminish V. So we can diminish V using a dielectric. And so let's take a look at some examples of that. So you could take a plate like this and a plate like this, and you could fill it with paper, actually. You could do that. You could, if you did that, then you would basically be increasing your epsilon naught to the value, give me a second, I'm looking it up. When you put in paper, epsilon naught goes up to 3.5 times epsilon naught. Okay? So that's if you put in paper. Then it becomes 3.5 epsilon naught. If we put in a special oil, you can make it 4.5% epsilon naught. If you put in something like porcelain, you can get it up to like 6.5 epsilon naught. And if you put in something like strontium titanate, you can make it 310 times epsilon naught. Okay, now here's the thing. These materials in the in-between here, those are called the dielectric, and you can see they all have different abilities to raise epsilon naught to new values. So you're not really changing epsilon naught, you're interfering with epsilon naught, and you're changing the effective permittivity of that region. Epsilon naught will always be what it is, but by timesing it by something, by putting in a material, you can times it by something. Okay? Now here's the thing. These all have different breakdowns though. Okay, so you got to be careful. So if your plate is charged up with too many volts, eventually oil will conduct, you see. So each of these dielectrics here have what's called a dielectric strength and eventually could break down under too much voltage and no longer supply a nice separation of charge. They then become a conduit for conduction. And you don't want that because then you lose your capacitance altogether. All right, so you can, in the book, look up the different dielectric constants. These are called kappas. Okay, these numbers in front are called kappas. And those are called the dielectric constants. And you can see it's specific to materials. But it basically effectively increases our capacitance because it upgrades our epsilon naught to higher by multiplying it by something. Okay, even water is quite a good one, but you have to be careful with the dielectric strength also. Like I was saying, these will eventually break down. Paper will conduct, oil will conduct, porcelain will conduct. Actually, polystyrene will be very hard to turn into a conductor, actually. It will resist conductivity quite well, but unfortunately has a very low kappa. So on the other hand, strontium titanate, has a very, very high dielectric constant, but listen, it breaks down. Okay, it breaks down and conducts before we want it to, perhaps. So you have to choose your materials and your voltages carefully with this sort of thing. All right, just a quick comment or two. There are polar dielectrics and also non-polar dielectrics, as mentioned in our book. Sometimes the goo that's between the plates actually has dipoles that can be readjusted. So the molecules in here might actually align themselves in the electric field direction. And when they do, they will affect the overall field in the region. Then there's other non-polar dielectrics, we call them, where they aren't really free to, they don't really have dipoles. So like, water is a dipolar thing. We talked about the whole hydrogen, oxygen thing, and little angle between them, and it's just kind of a natural dipole. So you could get that dipole to align in your medium there. But there are some substances that just aren't polar like that. They don't have dipole-looking molecules, but they can be induced. So like you might have like a molecule here, and it's not really dipolar, so it's not going to align. But because it feels the field from the plates, it will induce its own little dipole moment. So like let's say this top plate is positive compared to the bottom, you will find that it kind of polarizes itself in that sense. So it won't realign, but it will stretch, and it'll cause a slight dipole moment there as well. Okay, so that can also happen. So there are polar and non-polar dielectrics. Okay, the book talks about those things, and next time we'll talk about how we can use dielectrics while working with Gauss's law.